afternoon and good evening to folks who are joining us from other parts of the world. So I'll be talking about interpolation at arbitrary points in high-order meshes on GPUs. If you run a lot of simulations, you must have encountered this challenge, right? You'll interpolate at arbitrary points, either to query your solution for post-processing, exchanging information between overlapping grids and at inter-domain boundaries, or detecting contact between meshes. And this is a challenging problem, especially if you're dealing with unstructured curvilinear meshes distributed in HPC. Right? We see some examples here. We have the cubic mesh for the triple point problem, quadratic meshes for two overlapping grids, or linear meshes for contact. And if you're trying to figure out the dependency of where certain points are located in the mesh, it's going to be challenging. Okay. So how do we address this problem? To give you a quick background, following standard practice, mesh nodal positions in our framework are defined using a combination of nodal points in the reference space and basis functions. So for mesh nodes, the nodal points are Gauss-Lobato-Legendre points, and the basis functions are just Lagrange interpolants. And you see, if you use this combination, you get this summation. The first one shows the coefficients are the nodal locations in physical space. You have your basis functions for tensor product elements. You have n to the d nodes or basis functions where n is based on the polynomial order. And since we're using tensor product elements, we can use a product of 1D basis functions coming from each reference space direction, and that simplifies kind of this evaluation, and it's well suited for GPUs. Now, we use similar representation for our solution also. So you have velocity, temperature, right? It's represented similarly, which means if you want to interpolate your solution at any given physical location, you need to know the element that overlaps that point. You need to know, obviously, the MPI rank that the element is partitioned to, and you need to know the reference space coordinates inside the reference element corresponding to that. Okay. So our methodology to kind of figure this out or affect it is as follows. We have a one-time setup. So for a given mesh, we construct some maps, and what this map let us do is you give it a point, and it will tell you a list of MPI ranks that might contain the element overlapping the point. This is kind of a globally partitioned map. And then on each processor, we have a local map which gives you a list of elements that might contain the point. Now, once you get to that level and you have a list of elements, we have some bounding boxes pre-computed, which can help you quickly, read out the elements that are not going to be possible. And that gives us finally a list of a few elements that we want to look at. And in these elements, we solve a Newton minimization problem to figure out the reference space coordinates. And once we have those, we can just use the functional notation that I showed you from the previous slide to interpolate the solution. At this point, I want to highlight the implementation is based on this capability coming from GSLib, which was originally developed by James Lottis in the context of SEM for NEC 5000. I worked on it during my PhD to extend it for overlapping grids where a point might be located in multiple overlapping meshes. So you want to figure out the best source. And then when I came to the lab, I interfaced MFEM with it. And, obviously MFEM supports not just hexes. We have simplices, non-conforming meshes, not just continuous solution. We have different spaces for the entire DRAM complex, and we support all of that. But today I'm going to talk about our recent work where we support this capability on GPUs now. Okay. So beginning with the one-time setup, we first go, on each processor, we go over all the elements and construct an axis-aligned bounding box. So you see the example of the axis-aligned bounding box for one of the elements here, right? It just aligns with the axis. And essentially what we do is we take the nodal position function for each element, and figure out its extrema, both maximum and minimum for each direction. And this is not a trivial task. It's a high order function, so you can't just use point-wise values. So we have a methodology for figuring out the continuous maxima and minima. And once we do that for X, Y, Z, basically they give us the axis-aligned bounding box. And you can see in this animation the boxes for when you put the elements. Okay.
So in the curved case, you're doing a tight box.
Yeah. Yeah.
Because you can do the, I guess, the overestimation with like
Yeah.
Bayesian or something like that.
Right. Yeah. Now, while axis-aligned bounding box, have an advantage that they're easy to store and give a quick way to check if a given point is located in them or not. You can see that on the right or your left there, that you can use, there's a lot of waste of space here, right? Especially for curvilinear elements. So we need more compact boxes. That's where oriented bounding box come into picture. And the process is similar. Essentially, we take the element, but now first we rotate it so that it's aligned with the Cartesian axis. Then we figure out a bounding box for that element, and then rotate the bounding box to align with the original orientation. So that gives us the oriented bounding box, and you can see what it looks like. Yeah. Okay. Yeah. There you go. And the animation shows the oriented bounding box, and they end up being much more efficient. It's just that they need more space to store. And the check if a given point is located inside them or not is a little more expensive, but you'll see that they are helpful. Now, once you have the bounding boxes, our next step is to construct this map, which for a given point can give us a list of elements that, where the point might be located. So for that, we take our domain on that processor and fit a Cartesian aligned mesh. Okay, so in this case, we have 5 by 5 mesh. Ignore the type of NL equals to 8, right? And then we figure out the intersection of our mesh with this Cartesian aligned mesh. Now for high order elements, this intersection is not trivial to compute. So we do the intersection of axis aligned bounding box of each element with the mesh. Okay, and that's fairly easy to do. You just figure out where the diagonal corners of your box are located in the mesh, and you include all the elements in between. And we save this information in this multi-valued map, right? This multi-valued map basically tells for each element of the Cartesian mesh, what are the elements of our high order mesh that kind of intersected based on the bounding boxes. And then we can use this information during the find phase of our interpolation process, right? Where you have a given location and physical space coordinates. You figure out which element of the Cartesian mesh that point is located in, and then you use the map to get the list of elements. Okay. Now zooming out more, we have a similar map at the global level. We fit a Cartesian aligned mesh that spans the entire domain. Now the difference is that this Cartesian mesh is also partitioned across your n ranks, and we have to do some MPI communication to basically store this information, where we say which element of the Cartesian mesh overlaps with the elements of our high order mesh. But instead of saving the element indices of high order meshes, we just save the processor numbers or MPI rank index, right? And now you basically have this globally partitioned map that can take you first to the correct MPI ranks, and then you can use the local ranks to get the list of elements. And from there we go to the bounding boxes. So this is, as I said, this is the setup. It's a one-time setup for a given mesh. So if you're doing like a time-dependent problem where the mesh stays constant, you just do it once at the beginning, and then you can do interpolation as needed. For example, for Lagrangian particle tracking at every time step. Okay. Now the setup was, it ends up being a little communication intensive. So we still execute that on CPUs, but the next part is on GPUs. So first of all, there might be some data movement. You have your mesh nodes that might already be on GPU. If they're not, you're going to move them there. You have the local bounding boxes, which help you give the list of elements that are possible candidates for a given point. You have some information related to this local hash mesh, and then the coordinates of points to be found. And then finally, once we are done figuring out the element, we're going to return the output, which is going to be the element index, the reference space coordinates inside that element, distance between the actual point and the point that you found, and then a code which indicates whether a point was found inside an element on element boundary, which is relevant for interpolating functions in L2 spaces, or if a point was not found at all in case it was located outside the mesh. And wherever possible, we try to use coalesced access with shared memory for fast data access during of work arrays used with SIMD instructions. Okay, so the first thing that we do for a given point once we have the list of elements is we use this bounding box test. So you take your element, check if the point is located within its axis aligned bounding box or not. If it is not, you can discard that candidate. If it is, we take it to the second level, which is the oriented bounding box test. And that weeds out a lot of elements, right? If an element passes both the points, then we do our Newton's minimization. So our objective is basically this, L2 distance between the point that you're trying to find and the nodal position function, where you're trying to figure out the reference space coordinates. The initial guess here is based on the closest mesh node in physical space, and then we simply update it using the gradient and the second derivative of our objective function. Now we make sure that at each iteration we are staying within the reference element, and that the update or the delta R is within certain bounds based on a trust region scale factor. Okay, so we have our Jacobian and the Hessian here. The Hessian is kind of it's the most expensive to compute, right? You have a second derivative in the Hessian, and this term that you see highlighted with beta, it can have up to d cubed components in so that's like up to 27 components in 3D. So to kind of reduce the computational cost, we ignore this term when we are searching inside an element, and only include it if you're on the element boundary. And as I said, we use a trust region based approach. So alpha is determined after each Newton iteration based on the quality of the most recent update. Now, if we take the example where we are searching inside an element, as I said, since we ignore that second derivative term, the Newton update looks like the equation shown here. This means that for our evaluation, we need to compute delta x, which is it's the difference between the point you're trying to find and your current approximation, and the Jacobian of the transformation at that point. Now, for each point on our GPU, we assign a thread block, and each thread block has n times d threads. And this structure is specifically chosen because it maps well to the tensor product structure of a nodal position function. So for example, if you look at the equations here, you have in 2D of the x and y coordinate coming from the position function, or the Jacobian of the transformation. So you see there's a lot of summation over n terms, and the number of terms are a multiple of d, right? So we can parallelize our work across the different threads to do this efficiently. So and once we do every Newton update, we check if our current approximation is based on an element boundary or not. And as I mentioned earlier, if you're on element boundary, we do ignore that higher order derivative in the Hessian, and the cost is not that high. For example, in 2D, if you're on an element edge, one of the directions will be constrained. So that means you're left with just one term there. which is the derivative with respect to the r direction. Now, there can be cases where your points are not found locally. So you see two examples here. For example, the golden colored point here, it's located in your local hash mesh, but it's not located inside any element's bounding box. So that point, for example, will discard right away for search on that rank. Whereas the blue point, it's located in bounding box of one of the elements. So we're going to do a Newton search eventually, but we'll not really find it inside the element. We'll return instead the closest point on the element boundary and also the distance. And then when it's found within an element on another rank, eventually that will override the solution coming from this rank. Anyway, so that's basically our logic for finding out the element that overlaps a point and the corresponding reference space coordinates. Once we have that information, interpolation is easy. That's actually the easiest step. In this case, we assign like one thread block again for each point, and inside each block we have n to the d threads. That maps well to the tensor product structure that we have. And since a lot of processors are trying to do this concurrently, we first do it for all the points that are located locally on the elements that you own. Then we do the communication step, do another series of interpolation, and send the values back to the processors that queried the point. This past summer, we extended this to surface meshes with a student, Aditya. He's giving a talk in the next session. You'll find it interesting. Okay, moving on to the interesting part, the results. So this first example is, somewhat academic. We have a really high order element, 9th order spiral, and the idea is to just show you how fast this is. Okay.
Just to clarify, this is one element.
Yeah, just one element. But I love high order elements. Right. So in this case, we find up to, we start at 1,000 points and find up to 100 million points. Right. And you can see that you can find up to 1 million points in about 0.1 seconds. At 100 million points, it's taking about 10 seconds. This is an overkill, but still, you see how fast this is. And you see the timings here for both the find points phase and the interpolation phase. And, going back to our Newton's method, it takes about 5 Newton iterations on average per point. The solution here, the interpolation is basically it's the machine precision accuracy.
Does the Newton's method ever diverge?
Oh, it's so good. No, it depends on the initial guess. For really curvy elements, if your initial guess is not good enough, you might go to a local minima, but I'm putting in a fix for that because yeah. There's another example, the triple point problem. This has 65,000 elements, cubic mesh. The numbers here are coming from Lassen in our supercomputer here at LLNL with NVIDIA V100 chips. Now, typically, if you're running on one of the nodes, you would run on 4 GPUs. And before this work, the find points functionality would be executed on 4 CPU cores, right? But with the new kernels, you can see a comparison of how the GPU kernels can reduce your time to interpolation. Now, I will point out that since there's a lot of data movement, if you don't have enough points, right? If you're interpolating at very few points, it might just be faster to do it on CPU just because you're spending more time moving the data back and forth between, the host and the device. But as the number of points goes up, you see basically the GPU kernels shine. I had some surface Adi will be showing some results for surface meshes. And to show you some applications that are already leveraging find points in MFEM, we have a mini app that shows how you can solve PDEs on overlapping grids. Here we basically use find points to interpolate the boundary condition for each of the domains. So the solution, comes from the overlap from other overlapping meshes. You basically do this iteratively. You solve the PD independently on each domain, exchange the data, solve the PD, and repeat this process. And you can see in this figure on the right that you get a nice conforming solution. We also use this functionality for mesh-to-mesh remap during our adaptivity. So in this example, you have a uniform mesh, a discrete function with sharp gradients that obviously, this mesh is suboptimal for. And with TMOP, we can optimize this mesh to adapt to it. And during this our adaptivity process, after each neutron iteration, as the nodes move, we remap the field from your initial mesh to the current positions. Works pretty well. Some remarks on usage before we go to questions. So it's important that all MPI ranks call the method simultaneously. This is a common pitfall, because all the methods have global communication. So sometimes the user tries to do it on just one rank, and then they find that the process hangs. So just remember, all the methods have to call the method simultaneously. If you are using this for post-processing, please do not have the same set of points on all the ranks. This is also a common mistake where you are trying to calculate the drag by, you're querying the solution at 1,000,000 points on your surface. But just because of how we, write our logic for generating the sample points, basically, all the processors have the same list of 1,000,000 points, and you're doing a lot of work for nothing, right? In this case, just query the points from rank 0. It will take care of all the communication and return you all the interpolated values on rank 0. And finally, Veselin alluded to it. There's a lot of powerful things that we can do with this class now. Recently we had someone who wanted to do some custom interpolation, which did not directly leverage a grid function. In this case, we are able to still use GSLib to handle the communication, where we send the points to the ranks that own the elements overlapping them. And then you can interpolate whatever you want, right? Like it could be strain rate, tensor, gradients, whatever. You put them in a vector, give us back, and we'll take care of the communication, and then you'll have them back at the source. Okay, I want to thanks Johan for all the discussions this past year as I went on this journey to implement the GPU kernels. We now have robust arbitrary point search and high order meshes. In future, at some point, we'll be extending the implementation to simplices, and we have a paper coming out soon with all the technical details. Thanks.